Good morning, everyone, and welcome to the Thursday session. Today, we have a keynote speaker who needs very little introduction. Professor Mark Dry, University of Cape Town. When one thinks about the great challenges, technical challenges, and probably economic and political challenges of the past century, you have to refer to probably a couple of things that come to mind right away. One is food, and the other one is energy. In food, great challenge, of course, was the refertilization of the wasted soils, and thus immediately you think about ammonia synthesis and Haber-Bosch processes and so on. Energy for those countries and regions where liquid fuels, particularly for transportation uses, is not readily available off the ground, must come from some other source, and thus you think about other resources, and one of them is coal, and liquefaction and energy production of liquid fuels from coal has been a solution for some parts of the world, and particularly South Africa, and we know other regions of the world today that are starting to implement. We have essentially a person here who has been with the area of Fischer-Tropsch for entirely 50 years or so during the past century, and is continuing to be so during this century with a renewed emphasis. Professor Mark Dry got his education at South Africa Rhodes in Bristol in England, and spent 35 years involved in the development of process chemistry and engineering in the Fischer-Tropsch Sasol plant. Today he is here to talk about history as well as politics during the past 50 years. Professor Mark.
Well, I don't think I need you. Can you hear me at the back? I don't think I'll need it. Well, there won't be much politics. Okay, and in this talk, I'll confine myself to the more practical side of things. And I'll also show you several instances where things seem to go in cycles. The processes and schemes seem to be reinvented every 30 years or so. It's quite a common phenomenon. Let's start off by looking at some past and present Fischer-Tropsch plants, commercial plants only. In the 1940s, we had 9 German plants operating, and in the early 50s, there was a plant in Texas, Brownsville, which operated for a few years until it was shut down because of the price of methane went up. The 9 German plants, of course, were very inefficient, and they were simply shut down after the Second World War. Then the currently operating plants, the Sasol plants, the Moss gas plant in South Africa. The Moss gas plant, incidentally, is nothing to do with Sasol. It's a completely independent unit. We sell them some technology, and that's all. And then, of course, we had the Shell plant in Malaysia, which operated from 1993. So those are the current. If you look at the capacities, you notice the 9 German plants jointly produced capacity was 660 kilotons per annum, whereas the 3 Sasol plants, and it's mainly these 2 big plants, the capacity is now 7,500. So things have increased over the years. Now, the decision to build a Fischer-Tropsch plant depends on several things. Local politics is very important. The price of crude, or the perceived price of crude, and also the perceived reserves of crude oil. All these factors are involved when you decide to build a plant. Now, it can be a pretty tricky operation. Let me tell you about the Sasol 1 plant, the early plant which was constructed in the early 1950s. At that time, after the Second World War, there was a worldwide perception that the crude oil reserves were running dry. There was work done in America, work done in Germany, all on the Fischer-Tropsch process. And based on this perception, of course, it was predicted the price of crude would rise. And therefore, in South Africa, they decided, since we had huge coal reserves, and the price of crude was going to climb, we could put up a Fischer-Tropsch plant based on coal. It wasn't politics at that stage. Politics was only in the background, because at that stage there was no talk of oil embargoes. And so we built the plant. But in the middle of this construction, while they were actually constructing this plant, the huge oil reserves in the Middle East were discovered. And of course, this flattened the entire argument. The price of crude did not rise, so the Sasol one on paper was a bit of a flop. However, what saved Sasol one was the fact that they made high-priced linear waxes, which sold very well, and that we limped along for several years. Okay, but now let's look at the price of crude oil as it changes over the years. Now this is the vital factor. Long ago in the Sasol one day, we're back here, the price of crude was $5 a barrel. Very poor business. But in the mid-70s, as you all know, we had the Middle East oil crisis again, and the price of crude started going up, and Sasol decided by then they had developed all the technology they needed, and they decided to build new plants. And as luck would have it, when those two plants came on stream, the Sasol 2 and 3, they hit the jackpot. The price of crude was over $30 a barrel. So that at least was a success story. And as you can see, the price of crude has dropped again. And in 1992, about the Moss-Gas plant, it was designed here, and it came on stream there. Of course, that was a bit of a flop. And the Shell plants followed soon after. So as you can see, whereas the Sasol plants hit the jackpot, the Shell and the Moss-Gas plants did not. But look what's happened again just in the last year. It's shot up all the way to $30 a barrel, which once again it's sunk. What I'm trying to demonstrate is how tricky it is to decide to build or not to build a plant. Incidentally, on a personal note, it's also tricky to write about these things. In fact, a year ago, or 18 months ago, I wrote an article saying that at the current price of crude, $10 a barrel, it was completely unviable. And by the time it was published, the damn thing was $30. You can never know. Right, what is the cost breakdown of building a plant? The expensive business of building a plant is preparing the synthesis gas. That accounts for 65% of capital as well as running costs. The Fischer-Tropsch section itself, where you convert the synthesis gas to oils, this accounts for 25%, and then finally the refinery is only 10%, where you have to upgrade the fuels to make acceptable gasoline and acceptable diesel fuel. So you can see the price of crude, the syngas is the very important aspect here. Now because the syngas is so expensive, it's obviously important that you utilize it as efficiently as possible. And this means that the gas you feed to the reactor should match the so-called usage ratio that we just explained. Take the example of cobalt. The usage ratio is 2.1. This means 2.1 hydrogen reacts with the CO to form the building block CH2 plus a molecule of water. Now, in other words, you need to feed this ratio so that you can utilize all the gas because it's expensive to make. In the case of iron catalysts operating at 230, the usage ratio is lower. Now this is because of the water-gas shift reaction, which consumes some of the CO that you feed, it reacts with some of the hydrogen, the water vapor that you produce, and makes CO2, and it makes additional hydrogen. So overall, the usage ratio is 1.7. So ideally, you would like to feed a 1.7 ratio to a iron catalyst operating at low temperatures. But at high temperatures, the water-gas shift is very reactive. It goes rapidly in both directions. So you can either make CO2 or you can consume CO2 via the reverse water-gas shift. In the case of the iron catalyst at high temperatures, as long as your feed gas, the ratio of hydrogen divided by twice CO and 3 times CO2, as long as this ratio is about 1.1, you can theoretically consume all the gas you feed. But bear in mind, in a practical reactor, the pass conversion isn't 100%, but in practice you either have 2 stages or you have a recycle operation. But in practice you can consume all the gas. Now, in the preparation of syngas, we have two choices basically. You can gasify coal or you can gasify methane. Either way, the process is highly endothermic. This means you need to burn part of your feedstock to generate the energy to drive the reactions. In the case of coal gasification, 50% of the carbon in the coal ends up as CO2. You can see it seems terrible. In the case of methane, it's much better. Only about 20% ends up as CO2. Now, the inevitable result of this is that your carbon efficiency, of course, is poor. But as I say, that's simple chemistry. You can't get past that. The result, of course, of the coal versus methane is that in the case of a coal-based plant, the capital cost is 50% higher than in the case of a methane-based plant. We'll very rapidly give you some idea of the various options. This is the coal gasification procedure. You have coal being fed to the power plant with water, generates steam. The rest of the coal goes to gasification, plus steam, plus oxygen. And this is where the gasification process occurs. But because coal is hardly a clean feedstock, you get an amazing amount of byproducts. For instance, a lot of H2S is produced, which you have to selectively oxidize. You can't let it into the atmosphere. And you make pure sulfur. Yes. You get sulfur as a product. Then you generate a lot of pitch and aromatic oils, which are hydrofine, and they end up in the fuels or sell them as aromatic solvents. There's excess steam is passed into gasification. Because of this, there's a lot of water, which has to be, and this contains ammonia and phenols. And then you have to purify the water, of course, and that can go back into the cooling water system. Anyway, what I'm trying to get at here is a complex plant. There are lots of byproducts. You can sell all the byproducts. When you operate on a large scale, there's no problem selling these byproducts. But of course, it makes the plant very expensive to build in the first place. Now, in the case of methane, the situation is much better. This is the flow diagram of the moss gas plant in South Africa. Here they start with natural gas. You have a two-stage reforming, both catalytic, the primary reformers, the multitubular, followed by secondary reformers, and then you go to the Fischer-Tropsch process, and I won't go through all the plant, but you separate the products. The light end, which contains unconverted tail gas, together with methane and the C2s and the light ends, they are recycled to the secondary reformer and reconverted to syngas, so all the syngas is consumed. But obviously, it's simply natural gas reforming. There's a bit of scrubbing up here too, but it's a much simpler process and therefore cheaper to produce. The Shell plant in Malaysia is not that different from the moss gas plant, except that their natural gas is partially oxidized. This is a non-catalytic process, high temperature partial oxidation. And this produces a low ratio gas, lower than you need in the Fischer-Tropsch process. I'll come to a moment to figure how they fix that. So you have the partial oxidation, non-catalytic, goes to the Fischer-Tropsch process, and then all the light ends. In the Shell process, they don't want to recover things C4 and lighter. All the C4s, methane and C4s, are catalytically reformed, and this produces a higher ratio hydrogen-CO gas, so that here the hydrogen-CO matches what you want in there. You need about 2 in here, and you get it by blending these two streams. So that's the Shell plant in Malaysia. Now those are all the current ways of making syngas, but just for matter of interest, let me tell you what Exxon has proposed. They haven't got a commercial plant, but they have run large demonstration unit. They take natural gas, and here they use a fluidized bed catalytic reformer. Now the big deal about fluidized bed is that they are very efficient in terms of gas throughput. They have very good heat exchange, so you can make a huge amount of gas in the same size reactor. And because of that, the cost of producing syngas, which is the most expensive part, is apparently lowered considerably. But as a commercial plant is yet to appear. All right, now, as you all know, the bulk of chemicals and fuels in the world are dependent on carbon. And here I've simply listed the current, or a year ago or so, what the relative reserves are. If you call oil 1, then on an equivalent basis, methane is 1.5. In other words, there's a lot of methane around now all of a sudden. and coal is a massive 26. Now, even these figures can change. Let me take you back just to the 1970s, when there was a perception that methane was running out. And because Sasol had coal-based synthesis gas, we were asked to run pilot plant tests to convert this gas into methane over a standard nickel methanation catalyst. The runs were very successful. We showed that the gas was okay. And so Lurgi, who was involved with this, they designed a plant here in the States. I think it's Great Plains. The plant operated very well, etc., etc. But of course, the methane is plentiful now, so that's another case where things came and things went. Of course, now coming back to coal, one wonders, 26 times the reserve. Does this mean that we're going to get back to coal one day? Not in our time, I guess, but it's there. I'm not so sure about CO2 being so bad, but anyway, that's another subject. Right, now let's talk about Fischer-Tropsch reactors. We've now made this very expensive syngas, we have to convert it now. The reaction itself is highly exothermic. So the design of the reactors are important. We need good heat exchange systems. We have two operating modes basically, the so-called high temperature Fischer-Tropsch and the so-called low temperature Fischer-Tropsch. In the high temperature Fischer-Tropsch process, we are out to make gasoline and linear olefins. That's the objective. And the best reactors to use are the fluidized bed reactors. I'll be describing those. In the low temperature Fischer-Tropsch process, the objective is to make waxes. And the best reactors are the multitubular, or preferably the so-called slurry reactors. Now this is what we call the so-called circulating fluidized bed reactors, CFB. Excuse the slide, it's not very good, but the idea here is you have finely divided catalyst, iron-based, and here you have the dense phase fluidized catalyst moving down the standpipe with the control valve there, which controls the flow. The catalyst is then picked up by the incoming gas and it's swept around into that section where of course all the reaction occurs. And then the whole lot is conveyed to here to the wider section where, of course, because the reactor is wider there, the linear velocity of the gas drops and the catalyst is no longer being able to carry by the gas, so the catalyst drops down and the gas and the product go out by the cyclones. That's the so-called circulating fluidized bed reactor. These reactors were the original reactors built at Sasol 1. And they have operated very well for over 30 years. In fact, the Moss gas reactors are simply bigger versions of these. There's nothing wrong with those reactors, but they are very expensive to operate and expensive to build because they're huge reactors. A much better option is the so-called fixed fluidized bed reactors. And this is just a standard fluidized bed, as you probably know more usage. You have the feed coming into the bottom through specially designed gas distributors, and then you have this ebulliting, fast fluidized bed, but it's stationary. You know what I mean? It's bubbling around, but it doesn't go anywhere. And it's a much wider reactor, so the linear velocity is lower. This is a much cheaper and a much simpler reactor to build. Now, you can say, well, why on earth didn't Sasol put those up in the first place in the 1950s? Let's talk about the development of the FFB. I've mentioned the 1950 Brownsville plant in Texas ran a Fischer-Tropsch plant. They were, in fact, fixed fluidized bed reactors, and they were about 5 meters ID. Now, independently of that, Sasol had decided already to build the CFBs. I guess Kellogg's were better salesmen than the other people. But Sasol built the circulating fluidized bed reactors. Brownsville were operating these, and the rumors came back that the Brownsville plant was having fluidization problems. And that was true, but they solved the problem. But anyway, when we heard that they had problems, we of course were very pleased. You know, we'd chosen the right reactors. Okay, but now as it happens, the R&D pilot plants, which we used at Sasol to develop new catalysts and to investigate the various process variables, these plants were fixed fluidized beds. Pilot plants, admittedly, but they operated very well, and we started asking ourselves, why not fixed fluidized beds? So we went into fluidization studies based on the facts that browns will appear to have had problems. So we studied fluidization together with badgers, and in '84 we built a 1 meter ID demonstration unit, and it operated very well. In '89 we put up a 5 meter ID commercial unit, note the same size as Brownsville. And in the period of '95 to '99, all the large circulating fluidized bed reactors at the Sasol 2 and 3 plants were replaced by large fixed fluidized beds. So years typically, from 1950, it took 35 years before we were back to them. But they operated very well. We're very pleased with them. Now this gives you some idea of this is to the same scale. This is the fixed fluidized bed, that's the circulating fluidized bed. Same production capacity. You would see why this reactor is obviously a better deal price-wise. It's much cheaper to build. So just to rapidly summarize the main, just take a couple of key points here. I mentioned the fixed fluidized bed is 60% cheaper to build because it's so much smaller. It is a lower operating cost because the differential pressure over the bed is much lower, and therefore you don't spend so much energy pumping the gas around. And also the maintenance costs are lower, and this is because of the lower linear velocity again. In the circulating fluidized bed, you have abrasive ion catalyst traveling at meters per second, and at certain parts of the reactor you need to have ceramic lining, and you have to keep up maintenance. In these reactors, there's no need for that, much longer runs, so that in general they are much better reactors. And of course they have higher conversions as well, so that's lots of bonuses there. That's what the reactor looks like. Can't see much, but it's just a great big empty tube full of heat exchangers. Right, so much for the high temperature Fischer-Tropsch. Let's now have a look at the low temperature Fischer-Tropsch, where the objective is the production of waxes. The original Sasol reactors at Sasol 1, built in mid-1950s, were multi-tubular reactors. Those reactors are still there and they're still running. There's nothing wrong with that. But they're expensive to build because they consist of thousands of, in the case of the Sasol reactors, they're about 13 meters long and about 2-inch ID. And you have about 2,000 tubes per reactor. It's like a great big heat exchanger with catalyst in the tubes in the middle. So you have catalyst in the tubes, the gas flowing over, and water jackets around the intercontrol temperature. The shell reactors in Malaysia are the same type, but because they use Kobol catalyst, their tube diameters need to be much narrower. I guess they're around about 1 inch, and they're much bigger reactors. So they're still very expensive to build. But the point I want to make is these are expensive reactors to construct, but they operate very well. The alternative is, once again, a fluidized type reactor. I just call it a slurry reactor. It's actually a 3-phase reactor. In this case, you have the finely divided catalyst suspended in wax, liquid wax, under the synthesis conditions. So you're passing the syngas through a distributor plates, and then you just have a fluidized bed. And you can say, once again, how come these reactors, after all, were known? German scientist Kobol played around with this reactor soon after the war. How come it took us so long to build these reactors? The main reason is that because you have finely divided catalyst suspended in wax, and you are making wax, you need a very efficient system to separate the catalyst from the wax. After all, you want to end up with pure white wax, which you do. But the filtration, or the separation system rather, is a tricky one. And it took us several years to get that operating. But now it is operating, and it's working very well, Sasol. And what are the advantages of the slurry reactor over the multi-tubular reactor? I mentioned the cost is 75% cheaper to build. Just think of those thousands of tubes which have to be welded into these massive plates and things. It's a very expensive reactor. Often they just say the weight of the reactor is proportional to its cost. And big advantage of the slurry phase reactor is you can run longer times. This is because because it's the fluidized bed, you can remove catalyst, you can add catalyst online. So you don't have to shut down. In the case of a fixed fluidized bed, it's a massive performance. You have to shut the reactor down, open it up, get rid of the catalyst, recharge, and that takes you several days. And this is about the main. And of course, as I said, it's cheaper online, and also the operating costs are lower, once again, because the differential pressure of the reactor is low. It's a fluidized bed. You don't have to force gas through long, narrow pipes filled with catalyst. That's a picture of it. Well, you can't see very well. There's the fluidized slurry bed. The matter of interest in the background, there's one of the very old reactors, the circulating fluidized bed. Here's the wide hopper. There's the gooseneck, the standpipe is there. You can't see the reactor properly. It's behind the hopper. Okay, let's talk about the Fischer-Tropsch reaction itself. We've spoken about the hardware, and let's look inside. Let's have a look at the chemistry and the kinetics. I've emphasized that the cost of synthesis gas is very high. So once again, it's important that the selectivity of the process must be such that you maximize the amount of product you want to make. You want to make gasoline, you want to make a lot of gasoline, not just a little. You don't want to make methane, because that's what you're starting with most of the time. And the Fischer-Tropsch process, of course, makes a whole wide range of products. So selectivity is very important. And how do you control selectivity? The key factors are these. Temperature is an obvious one. The higher the temperature, the more methane you make. That's a bad direction. The catalyst type is important. You can either use iron or cobalt catalyst. Promoters are important in the case of iron. The alkali K2O is of vital importance. In fact, it is the key promoter. And then, of course, for both cobalt and iron, gas composition and also pressure play a role. Those are the variables that influence the selectivity of the process. Let's kick off by looking at the options you have for catalysts. These are 4 catalysts which are all potentially active Fischer-Tropsch catalysts. However, and this is the relative price. I've taken iron as 1. And I've cheated a bit here, but not cheated, because the fact is Sasol produces its catalyst from either mill scale, which is throwaway iron oxide from a neighboring steel plant, or it uses scrap iron to do it. So iron is dirt cheap. On the iron basis of 1, nickel is 250, cobalt is 1,000, and the ruthenium is a huge number. Now, nickel is too hydrogenated. You all know nickel is a very active hydrogenated catalyst. It makes far too much methane under typical Fischer-Tropsch conditions, so that's a no-no. Ruthenium is simply too expensive. In fact, there isn't enough ruthenium in any event. If you want to build more than 1 Fischer-Tropsch plant, you'll find you've exhausted the world's supply of ruthenium. So we're left with iron and we're left with cobalt. And you can see there's that huge price difference even there. Now, the Fischer-Tropsch process, I might have mentioned, makes a wide range of products. Under any conditions, you will make methane, you will make some high molecular weight waxes and oils. And when you play around with these variables that I mentioned, temperature, pressure, gas composition, you can shift the product distribution left to the right or whatever. You can shift it over wide ranges, but whatever you do, there is always a good interrelationship between the products. I take here for the high temperature Fischer-Tropsch process, I've plotted selectivity of methane, which is the undesired product, against some other cuts. Here's the gasoline, peaks around about just over 40, and then as the methane goes up, it falls off. There's the C3, there's the distillate or the diesel cut. You can see whatever you do, you can mess around with the catalyst, you can mess around with temperature, but somewhere these parts will always fall in place. The same goes for the low temperature process, where the objective is making wax. It's the same story. Here, wax is the desired product, and you can see as the wax selectivity shifts, all the others shift one way or the other. Most of them go through peaks and they're heavy. This is the gasoline that comes down. Now, how come we have these interrelationships? So neat. It's not higgledy-piggledy. There's some organization in the process somewhere. And this seems to be tied up with the, let us say, the process of chain growth. Let me just spend a minute here. You have carbon monoxide absorbing on the catalyst, and then somehow or other, no, I'm not going to go into this, you convert this CO to a CH2 unit, which you can consider the building block of the process. It's polymerization after that. Now let's rapidly go through this. You have the CH2 unit, it can either be hydrogenated to methane, or it can link up with another CH2 unit, the probability being alpha, to form a C2 unit. Now, the C2 unit, there's three options. It can either be hydrogenated to form ethane, or it can simply desorb to form ethylene. Or it can, once again, link up with another CH2 unit with the probability of alpha to form the C3 unit, and so on. And so it simply carries on. So you can consider it a polymerization process of CH2 units. Now, if it's as simple as that, if it's just a matter of probability of chain growth, you can, in fact, sit down and calculate the probabilities. You don't need to have to go through the whole exercise. If you assume the probability changes, and then you can, at each probability, you can calculate a product selectivity. And this is, in fact, this is a pure calculation. And you can see I've plotted probability from 0 to 1, and this is selectivity. Methane, typically, if the probability of chain growth is 0, obviously you only make methane. And then as the probability increases, the methane disappears, and the other extreme, the hard waxes appear. All other cuts in between methane and the very heavy waxes, all other cuts go through peaks. And you can see the gasoline peaks around about mid-40s, which matches the practice. The distillate or the diesel fuel peaks around about just about 20, and once again, that matches the actual observed phenomena. The only exceptions that are obvious is the C2 in practice is lower than the C2 predicted, and the methane usually is a bit higher. But otherwise, there's a surprisingly good correlation between the simple calculated value and the actual values observed in practice. Now, I'm putting this back up because I want to emphasize that there's not a mechanism. This is simply a polymerization procedure, if you wish. When I'm talking about mechanism, I mean this. How exactly does that CO molecule on an atom basis, on what is happening on the atomic scale, how does that convert to CH2? What exactly are the process steps? Does the CO dissociate and then this carbon reacts with hydrogen? Or do you first get an intermediate hydroxy process, which then ends up with CH2 with a further hydrogenation step? What is the actual nature of these intermediate complexes? And how exactly do they dissolve? What is their particular chemical process involved? This is what I mean by the basic mechanism. And there's an awful lot of argument about these mechanisms. People have been arguing about these mechanisms since Fischer-Tropsch started in the 1920s. And it's very interesting, but I keep on asking myself, is there any point in these arguments? Because I've yet to see anyone decide, right, we have 5 mechanisms, we've made our decision, mechanism B is the right mechanism. Based on this knowledge, we are now going to build a catalyst, make a catalyst that has a better activity, a better selectivity, and a longer life. I'm still waiting for that. Hopefully I'm wrong. But in the meantime, it's very interesting arguing about mechanisms. Now, coming back to the practical side of things, the Fischer-Tropsch plant is normally built at a fixed temperature and a fixed pressure, because that's it has to match the gas pressures and things like that. So that the temperature and pressures have been predetermined virtually. So what remains of interest is the correlation between the selectivity of the feed gas and the products coming out of the reactor. Now, obviously, as you pass gas into the reactor and you pass through the reactor, the composition changes. The partial pressures of the reactants change, and quite often the ratios of the reactants change, producing water and whatnot. So the man on the plant's not bothered with that. He wants to know if he feeds a certain gas, what's going to come out the other side of his reactor. So I'm going to give you some correlations which we can theorize about them, but in practice, you always establish the facts and you think about the reasons later on. This is the case for the low temperature Fischer-Tropsch process, where we're interested in making hard wax as the prime product. And here I've plotted simply the ratio of the hydrogen to CO of the gas entering the reactor. Now, in this case, in these particular, you can see there's a nice plot here, but here the pressure has been varied from 5 bar all the way to 60 bar. We've added water in some cases, in other cases we've added CO2, We've varied the recycle ratio, that means the tail gas that you recycle back to the fresh, you varied that ratio. We've varied catalyst loadings, and so in other words, space velocity has been changed. But in spite of all these variables, at the fixed temperature with the fixed catalyst, all you need to know is the ratio of the hydrogen to CO of the gas entering the reactor. It's clear-cut interrelation. That's for iron catalyst. For cobalt catalyst, incidentally, it's more or less the same, except that up to about 20 atmospheres, the methane decreases with increase in pressure. Because iron catalyst is independent of pressure from the low temperature process. For the high temperature process, it's a much more complex. So here I've used methane as a parameter because this is the undesired product. And here, this is the factor I'm using here at the gas entrance. Now it looks much more complex. If you take the simple hydrogen to CO ratio of the gas entering the reactor, it's a very poor correlation. In fact, there is no correlation virtually. Once again, here we varied the pressure from 10 bar all the way to 80 bar. We've added water, we've added CO2, changed the recycle ratio, changed the gas loadings and everything. And you can see this factor, for what it's worth, seems to be a reasonable correlation. This is the entrance of the gas composition. Now you can see because of the partial, because the hydrogen is to power 0.25, we can make it 0.5, it doesn't really matter much, it's a fractional power, and the CO is a power 1, you can see the pressure has an effect. In fact, if you increase the pressure in the high temperature process, the selectivity does change. This does not happen in the low temperature process. So this is the gas factor controlling selectivity. These are purely practical things. We can rationalize these things. You can say, what's CO2 doing there? Even though I mentioned that CO2 in fact doesn't influence the selectivity. If you keep all other parameters fixed and vary the CO2, you don't see much of a change. But yet you have got CO2 stuck in it. You can say, why? That's because of the water-gas shift reaction. The water-gas shift, the CO2 will obviously shift the thing one way or the other. So the CO2 has an indirect effect via the water-gas shift. And that's why it's stuck in there. Right, let's look at the kinetics. I'm just using two equations, which are pretty well accepted by a lot of people at least. For cobalt, we have this equation, and it only contains partial pressure of hydrogen and partial pressure of CO. There are only two factors involved. In the case of iron, you have the CO and the hydrogen partial pressure again. You also have a factor for the water vapor partial pressure. Now this fact that there's a water vapor partial pressure here and nothing there makes a tremendous difference. As you can realize, water is a product of the synthesis. Therefore, as you proceed through the reactor, you're obviously generating water, so the partial pressure of water is increasing, and this means the rate of the reaction is going to decrease because of the buildup of water in the system. And this will not happen theoretically, according to this reaction at least, it will not happen for cobalt catalysts. Now that makes a huge difference in the activity. Let me show you what I've done. I've had to do a bit of hocus-pocus matching here, but the point is you can make different catalysts with different activities. But to make the comparison valid, what I've done here, just look at the top blue line, which is cobalt catalyst operating at the 31 atmospheres about, and this is the iron catalyst operating at the same pressure. Now what I've done here is down here at the low conversion, I've deliberately chosen these parameters. The K value there and the M value here. I've deliberately matched those parameters such that, not matched them, I've adjusted them so that at low conversion you have the same activity. In other words, it's like operating the two catalysts in a differential reactor where the conversion is very low and the conversions, then the activity is the same. You produce the same amount of product. So in other words, I'm making the two catalysts, it's like making two catalysts of identical activity. Now let's see what happens afterwards. As you build up water vapor pressure, as you proceed down the bed length, and these are arbitrary units, and don't worry about the inches or feet or yards, the water vapor increases and the rate of the iron, in the case of the iron, sort of bends over. In the case of the cobalt, it carries on happily until very high conversion before it starts tipping over. And you can see, for instance, if you want to operate in this zone, there's a huge difference up here. the cobalt catalyst is capable intrinsically of converting or being much more reactive than iron. And there's no doubt about it. Cobalt is a more active catalyst. And one of the big reasons is it's less sensitive to the water vapor pressure. But this case here is the ideal case. I want to emphasize this. This, remember, assumes no water vapor effect. Now, there's a lot of work that's been done, including the CAER, that shows that water does depress the activity because, remember, a cobalt cap, because cobalt is so expensive, you have to minimize the loading of cobalt on your carrier. So you put as little as cobalt as possible, say, on alumina, and to get a decent activity, of course, you will need a high dispersion. This inevitably means very small crystals of cobalt. But very small crystals of cobalt have a different thermodynamics from bulk metal. So the small crystals oxidize. So you, in fact, knock out the very small crystals. So they are not active. And what's going to mean in practice, then, that this blue line is the optimum case where all the crystals are just the right size where they don't oxidize. But in practice, that's not likely to happen. So I would guess that the true blue line would probably run somewhere like there. But nevertheless, still will outperform the cobalt catalyst, the iron catalyst. Let's have a quick comparison between iron and cobalt. All the Sasol commercial units use iron. It's always been like that. But the new unit, the Shell plant uses cobalt catalyst, and the new slurry reactors, which have been designed for proposed plants, are all based on cobalt. Let's just quickly compare them. Cobalt, as I've mentioned, is much more expensive, but of course it's more active, so that's fine. Cobalt does deactivate, of course, like any other catalyst, and it's fairly slow. Now, iron deactivates faster, but it doesn't really matter because, remember, iron is so cheap, you can keep on charging fresh catalyst into the reactor and keep going at a high conversion. And that makes online addition viable for iron, but less viable for cobalt. And I've mentioned the fact that cobalt does have a problem of small crystals that oxidize, so so it's very important to optimize your particle size on the carrier. For iron, that's not all that important because it's so cheap. You have a huge surface area. You can use virtually pure iron in the catalyst, and you have a big surface area, and you oxidize, so what? You've got plenty of area to spare. Cobalt is more hydrogenated. This means it makes more methane. Because of that, you can only operate at low temperatures. As soon as you increase the temperature, the methane goes sky high. Iron being less hydrogenated means you make more olefins, which is nice, but it also means you can operate either at low temperatures or high temperatures. So iron has more versatility attached, but if you're interested in making long chain waxes, which are paraffinic, cobalt is fine. What about the future of Fischer-Tropsch? After all, the Sasol plants were built to make fuels. But since the price of crude doesn't look as though it's going to stay up very high anyway, for many years Sasol has been thinking of, well, they have moved towards chemicals. I think currently about 50% of the income comes from chemicals, no longer from fuels. Now the big deal about what I mean by chemicals, the Fischer-Tropsch process makes linear alpha olefins, which is a very valuable chemical. Of course, also the paraffins and the waxes are linear, which also sell as chemicals. Now, the advantage of the Fischer-Tropsch fuel is that they are environmentally friendly, which is a popular thing these days. Let's have a quick look at chemicals. We don't want to spend too much time here. Take the high temperature Fischer-Tropsch process. Let's just compare two cuts, the C6 cut and the C8 cut, just by way of example. The linear alkenes, linear alpha olefins, are 58% in the C6 cut, and the monomethyl 1-alkenes is still alpha olefin, but just one methyl branch is 24%. Now you can extract these linear alpha olefins quite easily by distillation processes and sell them, and they get co-polymerized with polyethylene to make the various grades of polyethylene. And Sasol is selling virtually all its C6 linear alpha olefins at very high prices. So that's good business now. Let's take the C10 cut, which is now being operated, being utilized as well. It contains 38% linear alpha olefins. and 20% of monomethyl 1-alkenes. In other words, when you add them up together, you've got 58% alpha olefins, which are essentially straight chain. And these you can convert in the so-called oxyl process, the hydroformylation, to produce virtually linear alcohols, which are used in the production of biodegradable detergents. So once again, you're in the chemical business. You're now competing with palm oil. And palm oil is nice and expensive, so you can sell things at good prices. Quick look at the fuels. I don't want to spend too much time on the gasoline because, remember, the Fischer-Tropsch process predominantly makes linear products, and this is bad news for gasoline. For high octane rating, you need branch products, you need aromatics. And the aromatics, even in a high temperature process, you do make some aromatics, but there's very little benzene. This is about 0.1% benzene, and the total aromatic is 5. So that sounds good, low aromatics, but of course the alkenes are far too high. They have to be hydrogenated, they have to be isomerized, the heavy naphtha has to be platinum reformed, and then you need to add some ether boosting octane number as well to make an acceptable, environmentally acceptable gasoline. It's a big performance to make. You can do it, Sasol does do it, but it's not cheap because you have to go through all these downstream production processes. A much better bet seems to be the production of distillate or diesel fuel. In this case, let's take the low temperature Fischer-Tropsch process, operating the slurry bed with cobalt. The total olefins will be only about 5%, so it needs very little hydrotreating to clean it up. There are no aromatics whatsoever in that diesel cut, and the cetane number is a beautiful 75. Remember, you only need about 45 in the marketplace. Of course, in general, all fuels in the Fischer-Tropsch process are free of sulfur and nitrogen, so that remains a plus in any event. Now, I want to say, because the diesel is a much better option, let's just concentrate on how do you make high-quality diesel from natural gas. Take the natural gas, you reform it catalytically. I've been through that. You make your syngas, you pass it through a Cobalt slurry reactor, and you operate this reactor at low temperatures deliberately to maximize wax production. You then take the wax and you hydroisomerize, hydrocrack it to produce distillate. You do produce quite a bit of naphtha, but that naphtha is useless as a gasoline because it's essentially straight chain, but it's a beautiful feedstock for thermal cracking to ethylene. You get very high yields of ethylene from it. And then, of course, if you need a purge somewhere, the light ends can be sent off to fuel gas. Now, this process, in fact, the Shell plant originally built their plant to produce wax, and then they cottoned onto the fact that you could produce the high-quality distillate. So they are operating their plant in two modes. Partly they're making wax, and the other section they are hydrocracking the wax to make distillate. Now, here's another case where things have reappeared after 25, 30 years. This whole concept is not new. Let me give you a bit of history. In the early 70s, we at Sasol, in the research department, we investigated wax hydrocracking. And we found that using the common catalyst like nickel moly on amorphous alumina, which is just, we took it just off the shelf, as it were, and we studied the hydrocracking. And we found we could produce, the product was 80% distillate, 15% naphtha, and about 5% of light ends. Now this is not surprising. If you simply do a simple calculation of beta scission cracking, that's what you get. And of course, all the stuff heavier than distillate, because it's the mild conditions, you don't get complete conversion. You recycle the heavier cut, and overall, you get 80% diesel. And it has a cetane number of close to 70. So it's excellent diesel stock. Now, taking you back, we knew this in the 1970s. In the mid-70s, Sasol had to decide, they were busy building Sasol 2 when they realized they wanted to double the capacity, so they had to decide what would the Sasol 3 look like. And we very boldly, maybe stupidly, suggested, let's build a hydrocracking plant. But they chucked it off the table, for good reasons though. Firstly, to make a lot of wax on a large scale would have meant at that stage to build a huge number of fixed bed multi-tubular reactors, which would have been very expensive. But the main reasons were economic. It was much better at that stage, in the 1970s, to make gasoline, because gasoline sold at a higher price than diesel. So gasoline was preferred in any event. They didn't want diesel. And also, very importantly, they were busy constructing Sasol 2 at the stage. So the workforce was on site. And the plans were there. So they simply duplicated the plant, which meant that they came on stream very rapidly. And of course, in doing that, they saved a tremendous amount of money. And as I say, they hit the jackpot when the oil was running at $30 a barrel. But now, 30 years later, Shell is doing this, and the plant that Sasol, together with Chevron, are putting up in Nigeria, will also virtually the same plant. Thank you. I'll leave it at that. Okay.
Thank you, Dr. Right, there is plenty of time for questions.
Mark, you mentioned using iron mill scale and scrap as a catalyst. My expectation is that there are a lot of alloying elements in those materials. This is not pure iron that's going into the system.
No, there's silica and a bit of chrome and things like that. Manganese is in it, but they are low levels.
Low levels, they do not build up within the reactors. There's essentially
no, because the iron being so cheap, you build up to go a little more deeper. There's so much carbon deposit in the high temperature fish. The small scale is used for making the fused iron catalyst. It's like an ammonia synthesis catalyst. You take the mill scale, you fuse it, and you add your promoters, and you just mill it up, reduce it, and there you are. But when you've done with it, and you've used it for a month or so, you just chuck it away. You don't bother to regenerate it. So there's no build-up of anything. You start every time with a fresh batch of catalyst. It's only when the catalyst is expensive that you need to recycle things. But iron is so cheap, the same goes for the low-temperature process. That's a precipitated iron catalyst. So it is more expensive to make, but we start with scrap iron of a certain composition, not any old scrap iron. But it's still scrap iron. You simply dissolve it in nitric acid, and there you have iron nitrate, and you carry on with the procedure. Is that on the question?
If one assumes high-octane gasoline is the goal, and you have, looks like you have a wide range of molecular weight products that you can produce, and if you begin to take into consideration isomerization, alkylation, reforming, hydration of the olefins to alcohols, it would seem to me that I haven't devoted any time to this study, but that it would be possible to come up with something kind of new, particularly if the goal is high-octane gasoline.
I've got to bear with me a minute. This is actually the Sasol plant. This is the large, the present operating Sasol plant. You have the fluidized-bed reactors. Now you have a whole range of products. Ethylene goes to polyethylene, we sell that. A lot of the propylene goes to also making polypropylene and ACN. But then the remaining C4s and the C3 olefins are oligomerized over a non-selective catalyst, just phosphoric acid ketone, and you make a highly branched product because of the mechanism. And so that the gasoline is highly branched, but also highly olefinic. But anyway, the octane rating and all that stuff's all right. But of course, the naphtha now being linear, having extracted the C5 to C8 linear alkenes, which you sell as chemicals, the rest is still pretty poor.
Isomerized and then
yes,
hydrated to iso alcohols.
Sasol doesn't isomerize the light end. Mosgas does. They isomerize the C5, C6, and they also make alkylate. But at Sasol, they simply take the remaining heavy naphtha and hydrofine it to get rid of the olefins and the alcohols and things, and then platinum reform to make gasoline. And then they also had MTBE and stuff like that. So you do end up with high octane gasoline, but it's quite a performance to make. Incidentally,
it depends on how things are in the world too.
Yes, sure. But what I'm getting at is, in general, you can make acceptable gasoline. Well, they do.
Can you vary that a little more so you push the molecular weight distribution even just a little farther to the right?
Well, the trouble is the way the plant operates, it's already operating on the maximum gasoline selectivity anyway. But you see, and even under those conditions, the C3 and C4 total accounts for about 20% of the product. So you have to, if you want to make a lot of gasoline, you have to oligomerize that.
Well, I think there's something between your low temperature and your high temperature.
Yes.
A little different process.
Yes, the high temperature is in fact at the peak of gasoline production anyway. So then you simply have to do something with the other cuts. And
I still don't see why you can't control molecular weight after you can complete the conversion. In other words, there's some ways to bring that molecular weight back down to where you want it to be.
Yeah, well, okay. Say
I was thinking
light
some
end
process in between.
you can crack the the
I was
wax.
saying something between making a lot of wax
Yes.
and
Yes.
making these olefins.
But you won't be at the gasoline peak then. You wouldn't. The straight run gasoline production would have already dropped down between the two. Incidentally, I've heard MTB is not a good thing these days, but since you make a lot of C3, you can of course convert that to diisopropyl ether, which is an alternative to.
Well, you can make isopropyl alcohol too.
Yeah.
And that's a high octane component.
Yeah, in fact, this is interesting.
People haven't worked on that very much.
No, the early days, Sasol always put, well, this is another cyclic argument. Originally, all the Sasol alcohol was about 5% alcohol produced in the process. I haven't mentioned that. It's in the water where they can recover the alcohols. But they added the alcohol to the petrol, and there were a lot of complaints about it because the carburetors of the old cars all got chewed up. And so they sold the alcohol to Brazil. But now the alcohol's back in again.
Yeah, that's what I was thinking. Thanks.
Other questions?
You mentioned briefly, and this is probably well known, that when you did the simple probability chain growth, that in actuality you make more methane and less ethane, or C2s. Why is that? Is there hydrodynamics?
Well, now we're into mechanisms and arguing about things. Well, we could say that C2, let's say, I'll give you an answer. Whether it's right is another matter. Let's say that that initial C2 complex, after all, it's a highly unsaturated species, it's bound to be very active. And you can get it in from all sides, right? So you can do hydrogenate it very easily, so you make a lot of it. Let's take the next, C2. An adsorbed, let's look at it as an adsorbed ethylene. You can add another C2 from either side, as it were, you know what I mean? There's no steric hindrance to add another CO2 to ethylene adsorbed. So you could say, well, because of the high amount of CH2 units on the surface, the ethylene will readily pick up another CH2 more than others and go on to the next complex. Now, once you've got to C3 and higher, you've got an absorbed olefin plus a side chain. Now you can say for steric reasons, that side chain is going to make it a little difficult for the C2 unit to get to that side of the molecule and come from the other side. Are you with me? And therefore the probability now has changed. So, and then from then on it doesn't matter. Now you have of course another alpha value. At higher values you have a so-called alpha 2, where the probability of chain growth is higher. There's some arguments about why that is. It reabsorption? Is it just longer residence time in the oil? Of course, under Fischer-Tropsch conditions, we have a liquid inside the pores. And the heavier liquids probably have a longer residence time inside the catalyst. And is it reabsorption or what have you? A lot of argument about that as well.
Other questions?
I have a simple question. I know nothing about Fischer-Tropsch. Have people tried, at least in experimental level, a mixture of cobalt iron catalyst?
Mixture?
Yeah.
Yes, well, I'm not sure. There have been some work on this, but there
Yeah,
has been some
Exxon.
work.
Is there any beneficial result because of?
Well, they got patents, so they had to find.
We never tried.
They ran out before they get
But they didn't run the pilot plant.
I know with cobalt you often put in a little ruthenium or platinum or something, so that's for different reasons, just to make the thing more hydrogenated and keep prevent oxidation and crack away the heavy ends that foul up the catalyst and things like that. But well, as far as Sasol is concerned, we either use cobalt or we use iron.
In terms of the economics, you said the natural gas base, of course, is much better. and yet if you take a natural gas that has a fair amount of ethane propane, it's better to do the cracking and preserve the carbon hydrogen content into making at least the ethylene propylene and C4s. And then for the methane, if the methane coupling ever becomes successful, you have a way of preserving the value rather than putting oxygen in and then taking oxygen out to make the hydrocarbons. Any thoughts which way you all lean?
Well, I get the impression in general that methane coupling is dead. I don't know. That's my impression. There seems to be a maximum. I get the impression the secondary product is more reactive than the primary product. Therefore, you just can't win. Your yields remain low. I forget the detail, but it's something like that. And my impression is that isn't this true? Is anyone working these days on methane coupling except for the oddballs?
Yeah, but aside from that, even if you're not doing taking the ethane propane out and making ethylene propylene C4s for the C2, C3 fraction is much more selective. And then only using the methane for making syngas.
Yeah. Well, the Moss gas plant, in fact, does. They call a wet gas, right?
Oh.
They do extract the lighter ends, and the C4s are alkylated. They are summarized to isobutane, then alkylated with the Fischer-Tropsch olefins.
Okay.
So that they don't send
the total natural.
They take C3s and heaviers is extracted. The C2s, there's only a little C2, and the methane and C2, so there's V4. That's the Moss gas plant. I should imagine Shell plant in Malaysia is similar.
In terms of the economics, you remove a lot of the motivation to develop new catalysts and so on. But anyways, what is the percentage of the operational cost that goes into catalysts?
I don't know, man. Fosco mentioned a figure, didn't he?
Yeah, he said that, it was $5 out of $10 operating cost was the cobalt catalyst.
But no, for iron, I would imagine it's very low. The fact that we chuck the stuff away shows you it's not worth it.
Yeah. Okay. Now, in terms of improving selectivity, microporous molecular sieve materials were worked on for a number of years.
Yes.
What is Sasso's position?
Well, I'm not over-convinced that they achieved much, as I recall. It's more or less, well, the two aspects. You can either make the stuff and then pass it over a microscope to sort of get selective cracking. But for iron, for instance, I've got the problem. You take the average sieve, you think it's acidic, right? And for iron catalyst, you need a basic promoter. So there's a contradiction. In fact, we just added some zeolite into the catalyst, and of course it's simply all the alkali migrated onto zeolite, and that is the end of the story. It just didn't perform. So for iron catalyst, the fact that there's silica and alumina, you need a balance. This is part of the formulation of the iron catalyst. I said potassium is the key promoter, which is correct, but if you have a lot of silica in the ore, potassium will react with the silica. You get silicates, which is less basic, so you need more alkali. But of course there's a limit. If the silica is very high, you just don't use that raw material. So there's interplay between the promoters. Now whether it's zeolite or silica or alumina, you've got to watch that. This is all part of, not the black art, but you've got to keep the right balance between the so-called structural promoters, or those which happen to be in the ore, and the amount of alkali you add.
Okay, so there are other reasons other than costs that come into play, not considering the transition metal in zeolite catalyst.
Yes, well, as I say, I don't get the. Mobile did quite a lot of work with zeolite and cobalt, but I don't get the impression that they were all that successful.
Well, the
I can remember high methane makes and things like that.
The Georgia Tech group did try to optimize the display.
How much methane do they make? But you know, if you start with methane, you don't want to make methane.
Yes.
So.
Where do you feel is parity between the gasoline derived from the Fischer-Tropsch whether it's natural gas or coal gas, versus the crude oil price. Is it 30 or 35?
I've heard the latest about $15. Then I've heard $17. Shastel seems to change his mind. I think every time that, the slurry reactor now, prices come down again. And there's another factor that makes it, because the diesel you produce in this wax hydrocracking process is such high quality, you can sell it at a premium. And this, of course, makes it a little more viable as well. So you bring that into it, I think you're talking about $15 a barrel, where you make 10% of your capital. I forget, I'm not an economist, but there's some magic number, what they call it. You know, you put your money in your bank, you get 10%, or you make 10%. Anyway, I think that point is about $15 a barrel at the moment.
I can tell you at Ashland, as we chase the value of a barrel of crude or shale oil or coal, as we chase that number, it always seemed to get away from us. It was always growing with the cost.
Well, the reason I was interested was from your perspective. You said 15 to 17. The number I hear in the U.S. and in Europe is again different. But in the U.S. it's more like $30 to $35.
Yes. Now this 15, by the way, is for virtually giveaway gas.
Oh, giveaway.
It's in case, you know, where these things considered is, say you have oil miles away, say Alaska, but there's a lot of methane attached to the oil, and you're not allowed to flare the stuff or burn it. So you have to do something with it. It's too expensive to pump back into the ground. In that case, your methane, in fact, could have a negative value. So you might as well convert it to oil and ship it along with the normal oil. In those cases, I think that's where the $15 comes from.
You bring up the stranded gas concept.
Sorry?
You just brought up the stranded gas concept.
Yes, that's right.
And a lot of people think that there's a future for FT in there.
Yeah.
But then you've got to put these plants at the wellhead, which sometimes brings in the thought of floating plants.
Yeah.
And then the second thing that's really upsetting to me is that you can take your numbers and throw them out, because the decision will be driven by regulation rather than economics.
Okay, let's thank again.
The ferry thing, I know, I visited this tar sand project some time ago, and they make massive amount of coke there. And I asked them what do they do with the coke. No, they're not allowed to gasify it to make too much CO2. So what do they do with the coke? They sell it in Japan to make CO2. What's the odds?
Okay, let's thank again.